Okay, so what if you could design life-saving drugs or create revolutionary new materials in like a fraction of the time it takes today? Today, we're going to dive into a discovery that might just do that, turning a really complex chemical puzzle into a solution that is just beautifully simple. All right, here's how we're going to break it down. First, we'll get a handle on the tiny matchmakers that are at the very heart of modern chemistry. Then, we'll look at a huge problem scientists have been bumping up against for years. After that, we get to the cool part, the brilliant solution they came up with, the proof that it actually works, and finally, we'll talk about why this whole thing is such a big deal for all of us. Just think for a second about the medicine that keeps us healthy, or even the screen you're looking at right this second. All these complex marvels are built by carefully, painstakingly stitching individual molecules together. But how does that molecular magic even happen? Well, this incredible molecular construction is all made possible by something called catalysts. And the best way to think about them is as tiny, tireless, molecular matchmakers. They basically grab the right molecules, bring them together, and help them form new bonds, speeding up reactions that might otherwise take, years, or maybe never even happen at all. Now, in this world of chemical matchmaking, there's one catalyst that is an absolute superstar. It's based on the element palladium, and it's the key player in what are known as cross-coupling reactions, which are frankly some of the most powerful tools chemists have for building really complex stuff. But, and there's always a but, right? Here's the catch. While these palladium catalysts are unbelievably powerful, actually making them has been a massive headache for chemists. It's been this huge bottleneck that just slows down the entire process of discovery. You see, the old way was just incredibly inefficient. If a chemist needed a slightly different catalyst for a new experiment, they had to start this whole clunky custom synthesis right from scratch. It was this tricky multi-step process that you had to do over and over and over again for every single little variation you wanted to try. And hey, don't just take my word for it. The researchers behind this breakthrough say it themselves. This need for a bespoke synthesis has basically limited the modularity and accessibility of these amazing tools. It's been throttling the pace of research for a long, long time. So here's the bottom line. Chemists were stuck in a world of bespoke tailoring, right? Where every single catalyst had to be custom-made. But what they desperately needed was a simple mix-and-match toolkit, something fast, reliable, and totally on-demand. Okay, so that's the problem. Now let's get to the really cool part, the breakthrough at the heart of this paper. The researchers came up with a solution to this long-standing problem that is just, it's surprisingly simple and elegant. The solution they found wasn't some crazy new machine or anything like that. It was this, an unassuming, kind of boring orange powder. This stable, easy-to-handle salt is a universal starting point, a single precursor that you can use to make countless different catalysts. And right here, you can see the sheer elegance of the solution on a molecular level. This robust, well-defined structure, this is what makes the whole thing possible. It's a compound that was specifically designed to be incredibly stable, which for the chemists using it just means simplicity and reliability. So the new process, it's just astonishingly simple. Compare this to the old way, right? You just take the universal powder off the shelf, you add a specific molecule called a ligand. That's kind of like the custom key for the specific reaction you want to run. And that's it. Your catalyst is ready to go in minutes, right at room temperature, no fuss. But of course, a new, simple method is only useful if it actually works, right? Can this quick mix-and-match approach really perform as well as the old, complicated, custom-made stuff? Let's take a look at the data. So in a head-to-head test for a really challenging chemical reaction, the results were just fantastic. The old catalyst, the one that was painstakingly prepared, gave us 76% yield. The new, on-demand method, 71%. That's practically identical. And it just blows other common alternatives completely out of the water. And if you're a visual person, this bar chart makes it even clearer. Just look at those two bars on the left. The performance of the new, simple method is obviously in the exact same league as the gold standard bespoke catalyst. It's a true drop-in replacement, but without any of the hassle. Okay, so the new method is just as good as the old one. We've established that. But then the researchers decided to really push the boundaries. Could their gentle, room temperature technique create a catalyst that was notoriously unstable? A catalyst that the old, harsher methods just couldn't make at all. And the answer was a resounding yes. Now, this This complex-looking spectrum here, this is the definitive proof. This shows they successfully made a catalyst that just falls apart under the conditions the old methods require. This proves the new approach doesn't just make things easier, it literally opens the door to entirely new chemical tools that were completely out of reach before. So what's the big picture impact here? I mean, what does it really mean for the future of chemistry when you can suddenly make these absolutely crucial tools so easily and so quickly? Well, this innovation is a game changer for how chemists work. It accelerates research because you can now screen hundreds of different catalysts in the time it used to take to make just one. It increases accessibility for more labs, and, like we just saw, it enables completely new discoveries by creating these previously elusive tools. So, if you're going to take away one thing, it's this. One simple bottle of orange powder sitting on a shelf can now do the job that used to require dozens of separate, difficult, and time-consuming procedures. It's just a massive leap forward in efficiency. And this leaves us with one last kind of provocative thought. By removing this huge bottleneck that has slowed down research for years, this new just-add-ligand method could unlock countless discoveries in medicine, in material science, you name it. The question isn't if this is going to lead to new breakthroughs, but rather what amazing discoveries have just been sitting there, waiting for a tool this simple to finally come along.